So we'll start by giving you a little bit of context and the objective of the study. So the context, maybe you all know it. So we have to decarbonize. So currently the shipping fleet, the container ship fleet is emitting a little bit above 200 megatons of CO2. And we have to reduce it to reach carbon neutrality by around 2050. So that is the objective set by the IMO. And we have two intermediate targets in 2030 and 2040. But it's not that easy because we have numerous changes. The first one is that we have high heterogeneity in the fleet. So in terms of vessel size, so we have very large difference in vessel size, but also in the operational profile of vessel, in terms of speed and time spent at sea, but also in terms of distance and the trip from regional to intercontinental trip. So we can't model the fleet by only considering one unique vessel. We have to distinguish between many vessels to account for this heterogeneity. We also have an heterogeneity in decarbonization options. So we can work on three axes. So the energy efficiency, the operational efficiency, and alternative energies. And for each of them, we have many solutions. The efficiency of these solutions will depend on the vessel. So we have both heterogeneities that are linked, and it's a system which is largely complex. And then we have to model the fact that we have a high inertia in the fleet renewal because the vessel will live a long time. So a vessel that is being built today will still be in operation in 2050. So we have to decarbonize from now and not in 5 or 10 years. We also have to deal with large uncertainties on a lot of parameters. So we have here some example. You can see here 5 traffic projections for the future. You can see here that we have a lot of uncertainties regarding the prices of energy or the prices of technologies. So for example, here the capex of engines. And we have to take this into account. So this is why we need to develop modeling tool because it's very difficult to find a clear pathway around all of this. So this is the idea of study. We want a modeling tool able to project emission pathways for a large fleet over years by 2050. This tool should be able to account for the heterogeneity. It should model the dynamics of the renewal and, in fact, the strong inertia. It should also model the penetration of low carbon technologies in the fleet, and finally to account for large uncertainties. So the case study of this work is the container ship fleet. And because the system and the model is highly complex, we have to put some assumptions. So we will only consider the low carbon technologies for the new built vessels. So in this work, there is no fuel switch or retrofit into for existing vessels. So the existing fleet still relies in fossil fuels. The fixed vessel lifetime at 30 years, so it will impact the pace of renewal, and we assume perfect foresight. So let's continue with the method. So the global model is composed of 2 modules. The first one will model the renewal of the fleet, and the second one will generate the emission pathways. So to model the fleet, we divided it in 13 segments. So based on the technical characteristics to account for heterogeneity. And each segment is represented by one reference vessel. So each vessel has technical characteristic, operational profile. Then we built the H pyramid for each segment. So all of this was made based on data from Clarkson Research. So for each segment, we have the H pyramid between 0 to 30 years, and it will help us to model the renewal of the fleet. So to model the dynamics, every year we have vessels that are becoming too old, so we will remove them from the fleet. We will build new ones, and to find how many vessels we have to build, the constraint is to meet yearly traffic demand, so expressed in ton-mile. That means that we are not replacing vessel in a one-for-one logic. We want to maintain the cargo capacity of the entire fleet. So it's possible to replace, for example, 2 small vessels by 1 larger. We just want to maintain the required cargo capacity. So this model is able to calculate for each year the number of vessels to build in each segment, and then to project the composition of the fleet. Then we need to discuss about the introduction of new technologies, because we want to discuss what are the conditions for them to enter into the fleet. So we discussed in this study alternative energies. We focused on e-fuels. So we choose to focus on methanol, hydrogen, ammonia, and the other low carbon technology studied here is the direct electrifications with batteries and electric motor. And then, so we have 6 possible technological solutions for the propulsive energy demand. And for the electrical energy demand of the ship, we have 5 main differences are here. So for the propulsion, we consider that the e-fuels are used in a dual fuel engine. For the electrical energy demand, we consider fuel cells. And regarding the energy and operational efficiency, we don't model individual technologies because it's really difficult to have a detailed model at the large scale, because technologies will depend on vessel, on operational profile, on geographical aspects. So we decided to introduce 3 frameworks regarding the energy efficiency improvements. So we have a pessimistic one where we consider that the vessel do not comply with EEDI or EEXI. We have a second one which is a little bit more optimistic because all the new built vessel will comply with EEDI. And the last one, the most optimistic, where all new built vessels comply with EEDI and all existing vessels comply with EEXI. And then we will discuss all the results across the 3 frameworks. So then we need to model the integration of low carbon technologies into the fleet. And for that, we assume that ship owners will always prioritize the least expensive solution. So this is why we are building a cost optimization model. This model aims to minimize the fleet renewal cost on a yearly basis. So this cost is the cost of building new vessels each year. It's composed of the capex of vessels, which depend on the vessel size and the technological configuration we used. The OPEX, which is the sum of the cost of energy and relative cost relative to an eventual carbon tax. And then we multiply it by the number of vessels to go from the vessel scale to the fleet scale. And it is the decision variable of the model. We want to know for each year how many vessels from segments S we will build with the technological configuration C. So how many vessels will be decarbonized and how many will still rely on fossil fuels. This model is deterministic. So if we give him a set of input parameters, so for example, energy prices, traffic demand, technological development, it will generate one pathway for emission. But as we discussed before, we need to take into account the uncertainties on input parameters. So this is why we generate a large amount of stochastic scenarios on the input parameters. So firstly, we did a literature review to identify which are the input parameters, which one are uncertain, and to define the range of variability for each of them. Then we could define probability density function for each parameter. Then we are able to generate more than 8,000 scenarios on input parameters and to do the simulations across the 3 frameworks. So you have here some example of stochastic of density function. So for example, for the prices of LNG, we assume conservative uniform distributions. And for the prices of e-fuels, we assume triangular distributions. So the boundaries are the boundaries of the literature, and the peak is the median value of the literature. So that brings us to the results. So the first thing that we wanted to do was to generate the emission pathways. So you have the results here. So you have here the emissions of the fleet and here the year. We modeled the pathways so across the three frameworks. The brown lines are all pathways where we applied no carbon tax, and the green lines are pathways where all new built vessels are using e-fuels. So you have here the most pessimistic pathways and here the decarbonized pathway. And we compared it to the objective of the IMO, so 2030 and 2040. So what we can remember from this figure, the first thing is that the EEDI and EEXI compliance help us because it will avoid a pathway like this where the emissions in 2050 are increasing. So the energy efficiency improvement can help us to at least control emissions by 2050 if we have no carbon tax. Regarding the objective, so we can see that here the 2030 objective is achievable, but under conditions. So we will to have full compliance with both EEDI and EEXI, and we should have a full integration of e-fuels in the new build fleet. So it's challenging, but it's feasible. And regarding the 2040 objective, we can see here that it is not mathematically feasible. The main reason is that we have a strong assumption about the existing fleet. So we consider there is no fuel switch in this fleet. And we find that under this condition, we can't achieve this objective. So we have to decarbonize also the existing fleet. So we have two solutions. We can introduce drop-in fuels or retrofit in the existing fleet to allow the vessels to use e-fuels, for example. Or we can imagine early decommissioning of vessels to accelerate the renewal pace and then to make the curve to be closer to the objective. Then we want to know what are the conditions to achieve ambitious reduction in 2050. So for the next part, we will focus only on pathways that are here in red. So that's all the pathways where emissions in 2050 are below 100 megatons of CO2. It represents a reduction of 50% relative to 2008. And we will discuss what are the energy requirements. So which amount of e-fuels we will need to produce, and so which amount of low carbon electricity we will need to have. So you have the results here for the amount of e-fuels that we want. So we will discuss for 3 years, 2030, 2040, and 2050, and again across the three frameworks. What we can see first is that the energy efficiency improvements help us because it can divide significantly the amount of energy that is needed. So it has two good consequences. Firstly, it makes the transition more feasible because we will need to produce less e-fuels, and we all know that it is difficult to produce these e-fuels. And secondly, it gives us a little bit more time to deploy a large-scale productions of e-fuels, because you can see that the requirements in 2030 are very low in this case. So we have more time, and it gives us a little bit of delay. So let's now enter into the results. So you have here the table that display all the data. So for each year, we have the amount of e-fuels that we need. We can calculate based on that the amount of low carbon electricity. So we consider an average conversion factor between hydrogen, ammonia, and methanol. And then we can imagine what is the solar capacity required to produce this amount of electricity, and the same for wind and nuclear. So what we can remember is that in 2030, to produce this amount of electricity, we will need to use 11% of the world's current capacity in solar energy, 8.5% for the wind capacity, and 3.6% for the nuclear capacity. So this data can be compared with this one. So currently, the container ship fleet energy consumptions only represent 0.40% of the global primary energy consumption. So it means that if in 2030 we use 11% of the world solar capacity only for the container ship, we will lack of carbon electricity, of low carbon electricity for the other sectors. So we want to be closer to this share in order to know that all other sectors will not lack of low carbon electricity if you use it for the container ships. We can also discuss the deployment pace that we will need between 2030 and 2050. So we will need to add between 60 to 80 terawatt hours per year of low carbon electricity. It represents between 7 to 16% of the current deployment pace, so based on data from 2022 to 2024. So once again, it's significant. And if we use all of this only for the container ship fleet, we will not have enough electricity to decarbonize other sectors. Then we can take a look at the most optimistic scenarios regarding energy efficiency. So in that case, in 2030, the amount of electricity needed is significantly reduced. So you can see that the share is more realistically feasible compared to this share. So it means that it appears that we will have enough electricity to produce the e-fuels, but it doesn't mean that we will have enough e-fuels because we still need to deploy the capacity to produce these e-fuels. And regarding the deployment pace, we can see that the amount is also reduced between 30 to 40 terawatt hours per year, but it still represents between 3 to 9% of the current deployment pace. So even in scenarios where we comply with EEDI and EEXI, we still need a large amount of electricity. So we need to improve the energy efficiency of vessels, or we need to deploy largely and more rapidly the capacity to produce low carbon electricity. So it's really challenging. So to finish, I will conclude by resuming what we saw. So firstly, we developed a model which is able to generate emission pathways for a large fleet. So here's the container ship fleets. This model accounts for the heterogeneity in the fleet, but also in decarbonization levels, and it deals with the large uncertainties regarding the input parameters. We saw that the path to achieve the 2030 IMO objective is feasible, but it will require full compliance with both EEDI and EEXI and full integration of e-fuels in the new build fleet. Regarding 2040, it will be largely more challenging because we can't focus only on the new build fleet. We have to deal also with the existing vessels, so with drop-in fuels or retrofits. And we can also imagine early decommissioning to accelerate the renewal pace of the fleet. And finally, we saw that the energy requirements are significant, and we will probably lack of low carbon electricity if we don't install more rapidly the production capacity. But the energy efficiency can help us by delaying the moment that we will need this energy, and it makes the transition more feasible, even if it's still very challenging. So thank you for your attention.